Good morning, everyone. Today we will discuss the design of the counterfort. In the previous lecture, we studied about the design of stem part of the retaining wall. In this lecture, we will be going to discuss the design of the counterfort part of the retaining wall. In order to design this counterfort, first of all, we must know its behavior. So, we know that the counterfort is the part which connects the stem and the heel portion. Now, we know that the stem portion is subjected to a lateral active earth pressure which acts in the leftward direction, and the heel portion is subjected to an effective pressure which acts in the downward direction. Now, this net effective earth pressure which is acting in the downward direction, this tries to deflect or bend the heel slab in the downward direction, in this fashion, and this lateral active earth pressure, this tries to deflect the stem in the leftward direction. And when this tries to happen, this original angle of 90 degrees, it tries to increase. But since these two components are connected by a counterfort, this increase of the angle is resisted by this counterfort, and in doing so, tension is induced in the counterfort along this sloping surface. Since tension is induced along this sloping surface, therefore the main reinforcement is provided along this sloping surface. Now, if you will look at this section from this side, this will look something like this. So this is the elevation of the wall when you are looking at this wall from this side. So when you will look at this wall from this side, it will look something like this. So this is the elevation, this is the heel slab, this is the counterfort, and these panels are of the stem portion. Now the counterfort, it acts as an inverted T-beam of varying rib. See, if you see this diagram, if I take the central part of this stem panel and the central part of this stem panel, this stem panel acts as the flange of the T-beam, and this counterfort, it acts as the web or rib of the T-beam with maximum depth at B, that is BB1 is the maximum depth of this counterfort. See, whenever there is a component with a sloping side, we find out the depth by taking a perpendicular to the sloping side. So if you draw a perpendicular from B to this sloping surface AC, this perpendicular will be maximum, that is BB1 will be maximum value, as compared to if you draw a perpendicular from any other point to this sloping line. So this counterfort, it behaves as the web of the T-beam with maximum depth as BB1. Now see, now if you look at this diagram, you will find that this counterfort is fixed at this base and it is free at the top. Therefore, this counterfort, it also acts as a cantilever structure, and in a cantilever structure we know that maximum bending moment and shear force are at the fixed support, and the bending moment is 0 at the free support. Or we can say that as we move away from the fixed support to the free end, the bending moment goes on decreasing. So in order to design the counterfort, first of all we will find out the maximum bending moment and shear force, and the maximum bending moment and shear force, we know that it is at the fixed end, that is BC. So first of all we will find out the values along the base of the counterfort. So if you see this diagram, you will see that this is the panel of the stem, and these panel, they act as a flange of the T-beam. Now whatever is the earth pressure, the lateral earth pressure acting on these stem part, these lateral earth pressure is transferred or carried by the counterforts. So first of all we will find out the bending moment at the base of the counterfort due to this lateral earth pressure. So in the previous calculations we already did the we already drew this earth pressure distribution diagram. The height of the stem was found out to be 8.9. So if the height of the stem is 8.9, the height of the counterfort will also be 8.9 meters, and at a depth of 8.9 meters, the earth pressure was found out to be 49.93 kilonewton per meter width. width. See, in the previous calculations, we found out the clear distance between the counterforts as 4 meters, and we also assumed the thickness of the counterforts to be zero point 0.6 meters. As we have taken the stem panel from center to center, so the center of 4 will be 2, so this will be 2, and the center of this stem panel will be 2, so 2 plus zero point 0.6 plus 2, so the total width of the stem will be 4.6 meters. So now we will find out the values of the maximum bending moment and shear force at this base. See, now we know the pressure distribution diagram. So first of all, we will convert this pressure distribution diagram into force. So how do we convert the pressure distribution diagram into force? Just take the area of this triangle. So the area of this triangle will be half base into height. So half base is 49.93 and the height is 8.9, and this force will act at the CG of the triangle, and the CG of triangle from the base is h by 3, that is 8.9 meters. So therefore the perpendicular distance will be h by 3. Now let's come to the calculations. Maximum bending moment will be at the base of the stem and the base slab, and this will be equal to C. And this is the area of the triangle. So when we take the area of the triangle, it will be converted into force, and this force will act at a height of h by 3 from the base. So the perpendicular distance will be h by 3. Now if you see this part, see, this value is 49.93 kilonewton per meter width. Now if you see this T-beam, the width of the flange is 4.6 meters. So the earth pressure is acting over a width of 4.6 meters. So we will multiply this 49.93 by the width in order to get the total earth pressure. So this 49.93 will be multiplied by 4.6, because 49.93 is in kilonewton per meter width. So we will have to multiply it with the width of the flange in order to get the total pressure. So after calculation, we will get the value of the bending moment to be 3032.13 kilonewton meter, and then the ultimate moment can be found out by 1.5 into m, which will come out to be 4548.20 kilonewton meter. Again, the maximum shear force will also be at the base of the counterfort retaining wall, and the shear force will be equal to the area to the force acting on the you can say that right part of this BC portion. So on the right part there is only one force, so this is triangular force. So convert this triangular area into force. So just take the area of this triangular portion, you will get the force. So again 49.93 is in kilonewton per meter, so multiply it with 4.6, so you will get the total shear force in kilonewton. So total shear force will come out to be 1022.07, and just multiply it with 1.5, you will get the ultimate shear force, that is the design shear force, that is 1533.10 kilonewtons. Now let's come to the next portion. Now we will find out the the total depth of the web. Now as we studied in the previous section, that the total depth of the web is the maximum perpendicular distance. So now we now have to find out this maximum perpendicular distance. So this is the retaining wall, this is the counterfort. Now we know this dimension is 0.3 meters. This height of the stem is 8.9 meters. This total length from the end of the heel up to the front face of the stem is 4 meters. So if this is 4 meter, this distance will be 3.7 meters. 4 minus 0.3, 3.7. So if I take this triangle, if you see this triangle, this triangle, if you see this triangle, so suppose this angle is theta angle. So if I take tan theta in this triangle, tan theta will be equal to perpendicular upon base. So perpendicular is 8.9, base is 3.7. So tan theta will be 8.9 divided by 3.7. Therefore theta will be equal to tan inverse of this. Therefore theta will come out to be 67.426 degrees. So now we have found out the value of theta. Now if you see this triangle, this angle is 90 degrees because this is a perpendicular on this slope. So this angle is 90 degrees. Now, if you see this triangle, now we have to find out this perpendicular DW. So if see perpendicular and we know the hypotenuse. So the relation between perpendicular and hypotenuse is sine theta. So if I take sine of theta, so it will be equal to perpendicular upon hypotenuse. Hypotenuse we know. See, this is 3.7 and this total width of the stem at the base is zero point 0.6. So if it is zero point 0.3, this width will be 0.3 meters. So if I subtract 0.3 from 3.7, I will get the base or the hypotenuse of this triangle, that is 3.4. So if I apply sine theta in this triangle, I will get the value of dW, which will come out to be 3.14 meters. Now the depth of the flange, see, the stem will act as a flange. Therefore, the depth of flange will be equal to the depth of stem. And see, now we will take the maximum depth of the stem, and the maximum depth of the stem is 0.6 at the base. So we will take the depth of flange as 0.6 meters. So if you see here, the total depth of the T cross section will be depth of web plus depth of flange. So if I add both the values, I will get the total depth of the T beam. After getting the total depth, suppose we are providing 20 mm dia bars and we are taking nominal cover as 50 mm. So the effective depth will be, see, if I subtract cover, the nominal cover and dia by 2 from the total depth, I will get the effective depth. So here I have taken all the values in meters. So 50 mm in meters will be 0.05 and 20 mm in meters will be 0.02. So after solving this, we will get 3.68 meters. So the value of effective depth has come out to be 3.68 meters. Now for this effective depth, we will now find the value of area of steel. See, if you see here, the effective depth is coming out to be 3.68. So this value is already 3.4 and this length is 3.7. So 3.68 will lie something here. So we can assume that the neutral axis, it lies in the flange part. So we are assuming that the neutral axis lies in the flange part, and that is the stem part of the retaining wall. So after this assumption, we will now find out the area of steel by this formula. See, now while putting the values in this formula, one point needed to be carefully noted down, that the width here will be the width of the web portion, and this effective depth will be the effective depth of the total T cross section. See, why we have taken the width of web? Because we are designing reinforcement for the counterfort, and this counterfort part, it behaves as the web of the counterfort retaining wall. Therefore we will provide BW width as BW, that is the width of web. So the width of web or the thickness of the counterfort is 600, we know that, and the effective depth we just have calculated, that is 3.68 meters. So we will take the values in mm, so this will be 3680 mm, and this mu which we calculated, see, that value was in kilonewton meters. So while putting here, we will have to convert it into Newton mm. So we will multiply it by 10 into 10 by 10 to the power 6. So after solving this, I will get the value of AST as 3542.80 mm. Now from this AST, we can find out the value of percentage steel. It will be 100 AST upon BW into D. So this will come out to be 0.16%, which is greater than minimum percentage of steel, that is 0.12 percentage. So therefore it is okay. Now we will provide 20 mm dia bars, which we already had assumed while calculating the effective depth. So the number of bars can be calculated by the total reinforcement divided by the area of one bar. So this will give you 12 bars. See, 12 bars cannot be provided in a single layer. So what we will do, we will provide these 12 bars in two layers with 6 bars in each layer. Now, see, now we know that as the height goes on increasing, the depth goes on decreasing. See, if you see this diagram, when we go up, the depth of this web, it goes on decreasing, and as the depth decreases, the bending moment will also go on decreasing. So the as the bending moment decreases, the reinforcement will also have to be reduced. So what we do is we provide reinforcement in three zones. So the reinforcement which we just calculated here, so this will be the reinforcement which will be provided near the B point, and for a height of h by 3, and after h by 3 the area of reinforcement will be decreased, and above again the area of reinforcement will be decreased, and the area of reinforcement will be calculated by this similar fashion. First we will have to calculate the depth at h by 3 height. Then we will continue with the same procedure, and then we will find out again we will find out the number of bars required, and then we will consider uh, 2 by 3h from the bottom, and then we will calculate the effective depth in there, and after putting the values, after doing the same procedure, we will again find out the values of number of bars. See, as we will go in the upward direction, the depth decreases, and the bending moment also goes on decreasing, because if you see here, if I take a depth of h by 3, so if I take a depth of h by 3, that is here, so at a depth of h by 3, the value of the pressure is also less, so the value of bending moment will also be less. And if you move again by h by 3, the value pressure will become more less. So as we move in the upward direction, the value of small d decreases, and also the value of bending moment also decreases. So we need to find out the values of d and mu at these height, and then again we will have to find out the number of bars by the same procedure that we did. I'm not going to solve for the number of bars in these two zones, that is for the next h by 3 and for the top h by 3. So you can do it by the same procedure that we did. So this is the number of reinforcement that we will provide for bending. Now in the next lecture I will discuss the calculation of the reinforcement for the shear force.